Good evening, students.
Good evening.
Good evening, sir.
Good evening, sir.
Good evening, all of you. So let us start with the discussion. Last class, this was the point of our discussion. At anode and cathode, we have prepared the respective H2 gas is produced at cathode, and at anode we have produced H2O2 by the electrolytic process. Right. So last point of a discussion left out in hydrogen is physical properties and chemical properties, and then we can go block to respect to S block. So physical properties of H2O2, it is a colorless, odorless liquid and impure with a bluish layer. One molecule of H2O2 forms greater number of hydrogen bonds than one molecule of water. If you think of H2O2, you have this type of structure: partial positive charge, partial negative charge, partial negative, partial positive. If you can look at one molecule of H2O2 forms great number of hydrogen bonds because of more like two oxygens are there with partial negative and two hydrogens with partial positive. So they will be developing new electrostatic attraction. They will be developing new electrostatic attractions with other H2O2 molecules because of a more number of hydrogen bonding. The boiling point is going to be high. So H2O2 will be having the highest boiling point, then D2O, and then finally H2O. Why D2O will have stronger boiling point? Because the OD bonds are stronger and electrostatic force of attraction developed between partial negatively charged oxygen and partial positively charged deuterium is going to be stronger. This is the correct order of boiling points of H2O2, D2O and H2O. And it is a dibasic acid because it can produce two H plus ions. It has oxidizing as well as reducing properties. This is also quite important. It has oxidizing as well as reducing properties. That means whenever H2O2 is acting as an oxidizing agent, H2O2, if it is acting as an oxidizing agent, in H2O2, what was the oxidation state of oxygen?
-1.
-1. It will be going, oxidizing agent will undergo reduction. So -1 to -2 state. That means H2O2 will be converting into H2O, where oxygen will be in the -2 state, where the charge, like the oxidation state of oxygen that has been reduced. Similarly, H2O2 can also be converting into respect to oxygen. H2O2, it is -1 state, and O2 in the oxygen, O2 oxygen is in 0 state. So this is how the conversion can also happen. This is H2O2 undergoing reduction, so it is acting as oxidizing agent. H2O2 undergoing oxidation, so it will be acting as a reducing agent. H2O2 can act as oxidizing agent as well as reducing agent because it is actually present in the intermediate oxidation state for oxygen. -1 to -2 or -1 to 0 can also be possible. H2O2 easily decomposes in the presence of light and temperature. So it is always kept in dark bottles and kept at cool places because in H2O2 we have peroxy linkage. Due to peroxy linkage, what happens? The repulsions are going to be high. So 2H2O2 will be forming respect to 2H2O. 2H2O2 gives 2H2O plus O2. This is how the balancing is going to be happening, and this reaction is going to happen at high temperature. 30% solution of H2O2, that is called as perhydral. 30% solution of H2O2, that is also called as perhydral. Right. Chemical properties. Yes, very good. Chemical properties, if you look at, as I have told you, H2O2 has oxidizing as well as reducing nature. H2O2 can try to oxidize respect to Fe plus 2 to Fe plus 3. NO2 minus, nitrogen is which state? NO2 minus, oxidation state 1 into X plus 2 into -2 is equals to -1. X is equal to plus 3. From plus 3 to plus 5 state, nitrogen has been increased. Sulfur from 0 to plus 6 state. The oxidation states of Fe, nitrogen and sulfur has been increased. So H2O2 is actually acting as a reducing agent. H2O2 will be acting as a respective reducing agent. Right? H2O2 is acting as an oxidizing agent, so it will undergoing reduction. It is also acting as a reducing agent, so it will undergo oxidation. So these are the typical reaction. Like wherever it is acting as oxidizing agent, it itself will undergo reduction. wherever it is acting as a reducing agent, it itself will undergo oxidation. Okay. So these are the respective reactions. MnO4 minus in the presence of acidic medium form Mn plus 2, MnO4 minus in OH minus form Mn plus 4. So H2O2, the oxygen is going to be converting into respect to O2, where -1 to 0 has been the oxidation state conversion. Structure of hydrogen peroxide. You have to study the structure of hydrogen peroxide in two phases. What are two phases which you can think of is gas phase as well as solid phase. Hydrogen peroxide will have like half open book structure. If you try to open a book, not completely, just half, then you will be having the structure left out that will be similar to the structure of H2O2. H2O2 will have half open book structure. In the solid state and in the gas phase, the OH bond lengths and O bond lengths, they are going to be differed. It has half open book structure. It has a non-planar structure. In the gas phase, if you try to think of, as well as in the solid phase, you have oxygen-oxygen bond, OH bond, oxygen-oxygen bond, OH bond. OH bond length in the gas phase is 95 picometer, whereas OH bond length in the solid phase is 98. So in the solid phase, you have greater OH bond length when compared to gas phase, whereas oxygen-oxygen bond length, that will be greater in the gas phase when compared to the solid phase. Oxygen-oxygen bond length is greater in the gas phase when compared to solid phase, because in a solid phase, the oxygen will fit at the respective crystal sites. In the solid phase, these oxygen atoms will be fitting at the crystal sites, thereby the bond length will be smaller, the bond energy would be greater. Whereas OH bonds are going to be larger in the solid phase when compared to the gaseous phase. Is that clear?
Yes, sir.
Yes.
Yes, right. Uses of hydrogen peroxide, it is actually used as bleaching agent because H2O2 upon decomposition it gives H2O plus nascent oxygen. So because of this reaction, this oxygen is going to add it to a colored substance and make the substance uncolored. So that is why this is acting as a bleaching agent and antiseptic. H2O2 plus N2H4. N2H4 is NH2, NH2. H2O2 combined with hydrogen, it is used as a rocket propellant and it is also used in hair bleaching. These are some of the properties or you can say some of the uses of H2O2. These are some of the uses of respect to hydrogen peroxide. Try to solve this question. H2O2 is not used as oxidant, reductant, bleaching agent, antiseptic, dehydrating agent.
Dehydrating.
It is not used as dehydrating agent. That is the right option. The correct order of boiling point is H2,
H2O2, D2O,
H2O2 greater than, then D2O, then H2O. This is the right option. Yes. So this is all about your hydrogen and its compounds. So let us start with the next chapter, that is S block, group 1 as well as group 2. So S block, we have two groups in S block, students. Group 1 as well as group 2, and we all know hydrogen shows similarities with the group 1 as well as group 17. That is why it is placed separately at the center of the periodic table. This is your S block, then you have D block and P block, and at the bottom you have respect to F block. F block actually belongs to the third group itself, like from 58 to 71. After lanthanum, whatever the 14 elements you have, they are said to be lanthanides. After actinium, whatever the 14 elements you have, they are said to be actinides. So we are now studying or concentrating on the S block, that is group 1 and group 2. S block elements, if you try to look at them, they are all S block elements, they are all
Metals.
like metals, electropositive in nature. And group 1, what are the elements we have? Lithium, sodium, potassium, rubidium, cesium, and francium. Group 2, what do you have? Beryllium, magnesium, calcium,
Beryllium.
strontium, barium, as well as radium. Yes or no? S block, lithium, sodium, potassium, rubidium, cesium, francium. Group 2, beryllium, magnesium, calcium, strontium, barium, and radium. So these are the respective names of group 1 as well as group 2 elements. S block are also called as
Alkali metals.
S block elements. They are also called as alkali metals. As group 1A are called as alkali metals. Group 2A
Alkali earth metals.
metals. Right, very good. So 1A and 2A alkali metals. If you try to write the electronic configuration of alkali metals like lithium, sodium, potassium, you will have outermost electronic configuration will have one electron because they are filled after the inert gas of the previous period. Immediately one electron when you try to fill, you will get an respective alkali metal. Electronic configuration will be NS1. Alkaline earth metal electronic configuration will be NS2. Alkali metal oxidation state, because upon losing one electron, it forms the inert gas configuration of the previous period. So it will be having respect to +1 as the oxidation state, whereas alkaline earth metals they will have +2 states. And in the group 1 and group 2, we have radioactive elements. That is, what is the radioactive element in group 1?
Francium.
Francium. And in group 2, you have respective radium. And they are soft, light, malleable, and ductile. Group 1 elements, they are actually soft, light, malleable, and ductile. And group 2, they are actually harder than group 1. Why? If you try to think of metallic bonding depends upon what?
Size between atoms.
Yes, metallic bonding is directly proportional to, metallic bonding is the electrostatic force of attraction between metal kernels and all the unpaired electrons or the free electrons. Every group 2 element like metal, it will give M2 plus 2 electrons. So more number of free electrons are given out, whereas group 1 will be giving only 1 electron. More number of free electrons, more will be the metallic bonding. So metallic bonding is directly proportional to number of free electrons, as it is defined as electrostatic force of attraction between metal kernels and all the free electrons. Metal kernels and all the free electrons, right? Metal is going to be paramagnetic, whereas metal is going to be diamagnetic here. Why? Because we have only one electron in the in the S subshell. We have only one electron because of the presence of unpaired electron. Because of the presence of unpaired electron, the metal is going to be respect to paramagnetic. Whereas in the group 2A, metal is going to be diamagnetic. Because of diamagnetic nature, it is going to have, obviously because of no unpaired electron, it will be diamagnetic in nature. No unpaired electron. No unpaired electron in the group 2A, whereas there is an unpaired electron in the respective group 1A. Respect to metal ions, if you talk of metal, metal is going to be paramagnetic, alkali metal. Alkaline earth metal is diamagnetic. If you talk of metal ions are actually diamagnetic in both the cases, because the metal ion here will also have inert gas configuration, and M2 plus in the alkaline earth metal, that will also have the inert gas configuration. Is that clear, students? Yes, right.
Sir.
So we will study different properties now. Atomic radius, melting point and boiling point, electropositive character, photoelectric effect, densities, flame test, ionization potentials, conductivity. All these we are going to study for the group 1 as well as to group 2. That means comparative study we have to do. Comparatively have studied the respective group 1 and group 2. Atomic radius, first talk of atomic size. When you go with the atomic size, what happens from top to bottom?
Increases.
Size increases because the electrons are entering the next high range level. So you can say lithium, sodium, potassium, rubidium, cesium, francium. So from top to bottom, size increases in the group 1 as well as in group 2. Size is going to be increasing. You compare between group 1 and group 2. Which has
Group
more
2.
size?
Group 1 is more size.
Because in group 2, what happens? Effective nuclear charge has been increased or not? In group 2, since we are adding electrons, like in the same period, we are adding the electrons. Obviously, the protons are also added. Obviously, the effective nuclear charge is going to be increased when you go from lithium to beryllium. Because of increased nuclear charge, what happens? Size will be decreasing. Atomic size increases from top to bottom in a group and decreases from left to right in a period. So combinedly, if you try to study, you will have this order. Lithium will be the least. After lithium, you have this type of order. Lithium will be least. Beryllium will be least. Beryllium. After beryllium, you have lithium. After lithium, you will be having magnesium. After magnesium, you have respect to sodium. After sodium, you will have respect to calcium. From calcium to strontium, strontium to barium. Like after calcium, you have strontium. After strontium, you have barium. After barium, again you have potassium. Potassium to rubidium, rubidium to cesium. We are eliminating these two because they are radioactive in nature. So what is the size order now? Try to compare. Cesium is going to be highest, then rubidium, then potassium, then barium, then strontium, then calcium, sodium, magnesium, lithium, and least is going to be beryllium. Is that clear or not? Yes, beryllium is going to be respect to smallest, and cesium is going to be the respect to largest. And if you try to compare cesium, then rubidium, potassium, barium, strontium, calcium, sodium, magnesium, lithium, and beryllium, these are compared to study. This is a combined effect, like from top to bottom, atomic size should increase. From left to right, increased effective nuclear charge will decrease the size. Combined effect of these two, we are comparing between 1A and 2A. Right?
Yes, sir.
Yes. Beryllium is going to be least. And then you have lithium. Lithium to magnesium, magnesium to respect to sodium, sodium to calcium, calcium to strontium, strontium to barium, barium to potassium, then rubidium, and then finally cesium. So this was the correct size comparison of both group 1A as well as group 2A. Ionization potentials you try to compare. In the group 1A, how the size is going to be varying? Lithium least, then sodium, potassium, rubidium, cesium. In the group 2A,
Beryllium, magnesium, calcium, strontium.
beryllium least, then magnesium, then calcium, then strontium, and then barium. Ionization potential in the group 1A or in the group 2A, there was no exception with respect to size, so there won't be any exception with respect to ionization potential also. Ionization potential is inversely proportional to atomic size. As size increases, what is going to happen?
Ionization potential decreases and shielding effect increases.
Yes, as size increases, the outermost electron can be easily removed out because that will be having very less electrostatic force of attraction with the nucleus. So as the atomic size increases, the outermost electron, whatever you have, right, that can be easily removed from the respective atom because of less electrostatic force of attraction. So lithium greater than sodium greater than potassium, rubidium, cesium, and beryllium greater than magnesium greater than calcium greater than strontium greater than barium. This was the respective ionization potential orders. This was the respective ionization potential orders of group 1A as well as group 2A. Right. Now try to look at the next concept, melting point and boiling point. Melting point and boiling point depends upon what?
Size.
Melting point and boiling point depends upon metallic nature. Yes or no? Melting point and boiling point, they depend upon the metallic nature. and lower melting point and higher melting. How to compare this melting point? Like where you have metallic bond greater, stronger metal, like these are all metals, right? These are all metals. You have respect to metals, in the respect to metals, what do you have? Crystal
Metal
latticite.
kernel.
Yes, crystal latticettes, and you have metal kernels Mn plus. What is metallic bond? Melting point and boiling point, they obviously should be directly proportional to strength of metallic bond for metal. Metallic bonding should be proportional to what?
Number of
Number
electron
of
release.
free electrons in the metal lattice. We are not going to say directly unpaired electrons, because how many free electrons are there between the metal kernel and all the free electrons? Whatever the electrostatic force of attraction is developed, that is deciding the respect to metallic bonding. When compared to 1A and 2A, which will have more number of free electrons?
2A.
2A.
2A. Obviously 2A will have stronger melting point because stronger metallic bonding. So melting point and boiling point for 2A is greater when compared to 1A. But within 1A and within 2A, you try to compare. Within 1A, you compare. So the same Li plus K, Li plus Na plus K plus Rb plus Cs plus. If you go from top to bottom, Li plus
Metallic character increases.
Na plus, like strength of metallic bond, you try to compare. The plus 1 charge is present here. The Na plus will have plus 1 charge here. Same electron, same number of electrons, same number of electron. K plus, where the strength of metallic bond is greater. For Li plus, we have stronger bond, or for last, we have stronger bond for Cs plus.
Li plus.
Li plus, because of small size, what you can say, the metallic bond is going to be directly proportional or not. Strength of metallic bond will be depending upon number of free electrons which are obtained in the metal crystal lattice of metal. And also, if you go from top to bottom, size is increasing. If the size is increasing, for cesium we can have what? Very large size cesium with a plus 1 charge only and electron. So the plus 1 charge is present in this much size, and only one electron, same number of electrons are present everywhere. So electrostatic force of attraction is going to be decreased. Since Li plus will have many more charge density, that will be developing great electrostatic force of attraction. Because of that, the strength of metallic bonding is going to be high in the case of lithium. So lithium will be having the respect to greater melting point. Yes or no? Lithium greater, then sodium, then potassium, then rubidium. Sodium, potassium, rubidium, and then finally least is going to be cesium. With the same logic, what you have to say? For this is for 1A. When compared to 1A and 2A, 2A is much higher. But within 2A, how to compare? Beryllium, magnesium, calcium, strontium, barium. But exception with respect to beryllium, beryllium will be having the low melting point or boiling point. Why? Because the crystal structure of beryllium is not compact. Why? Because of its radius ratio calculations. Okay, is that clear or not? So metallic melting point and boiling point directly proportional to strength of metallic bond. Strength of metallic bonding is directly proportional to number of valence electrons, because those are the free electrons in the crystal lattice structure, and also inversely proportional to size of atom. So low melting point when compared to 2A, higher than 1A. Lithium greater than sodium, greater than potassium, greater than rubidium, greater than cesium. In the 2A, what you have? Beryllium. After beryllium, you are not having magnesium. Magnesium is least. Magnesium has low melting point or boiling point in its group. As its crystal structure is not compact. Magnesium has low melting point or boiling point because its crystal structure is not compact. That is no proper, like whenever the crystal structure is great, then only we have higher melting point or boiling point. That is not there for magnesium. Photoelectric effect. Photoelectric effect is shown by 1A elements or 2A elements both.
Both.
So where you will have photoelectric effect. Photoelectric effect means what? Whenever we have a metal, on the
Electrons
metal you irradiate electromagnetic radiation. That electromagnetic radiation has to remove the electron from the metal. Like from 1A, and from where the electron can be easily removed?
cesium.
Cesium, potassium, rubidium, only these three elements will be showing the photoelectric effect in the 1A. In the 1A, lithium or sodium will not show, and also in 2A, no element will be showing the photoelectric effect, because whatever the electromagnetic radiation we are giving, that radiation cannot remove the electron, as ionization energy values are going to be high for 2A elements. Okay. Generally, only few elements will show. Potassium, rubidium, cesium shows photoelectric effect due to low ionization energy values. No element shows photoelectric effect due to high ionization values in the 2A. You may ask a question, sir, I will be giving the radiation in such a way such that electron can be removed out. In that cases, you can remove the electron. Ionization potential is mentioned, no. But with the radiation, the easy removal of electron is going to happen only when the ionization energy is low. So only potassium, rubidium, cesium can be showing the photoelectric effect to a greater extent, because easily the electron come out. Density calculations. Density is equals to mass by volume. Density of atom is nothing but mass of atom by volume of atom. Generally, what happened to the density? From top to bottom,
Decreases moving right. Decreases.
decreases or increases? Density is equals to mass by volume, right? Mass is going to be increasing greatly or not?
Yes, sir.
Yes or no? Density is equals to mass by volume. Generally, density should be increasing. General trend. Generally, because the increase in the mass is much higher. Generally, density increases down the group. So we should have what? Lithium. After lithium, you should have sodium, but you have potassium. Why? Because of sudden increase in size, potassium has less density than sodium. Because of, like, up to lithium and sodium, we are filling only. In the lithium and sodium, we are only filling what? We are only filling 1s, 2s, yes or no? But in the potassium, we are entering the third level where we also have d orbitals. Although we are not filling the d orbitals in the potassium, but what happens? The sudden increase in the size can be seen from sodium to potassium because of sudden increase in size. Potassium has less density than sodium, and also in the potassium we have vacant orbitals. Yes or no? These are the reasons. Density of beryllium, same exception you can see with respect to magnesium and beryllium. Density of beryllium is higher than calcium and magnesium because of less volume in comparison to its size. So first elements, they are going to be having least volume. So calcium least in the density, then magnesium. After magnesium, you have like we have, this is the general order: beryllium, magnesium, calcium, strontium, barium. This is general trend. But you have seen the exception with respect to calcium and magnesium. So calcium is going to be having less density when compared to magnesium, same as potassium has less density than sodium. But beryllium will be having more density than magnesium also. Beryllium will be having more density. Like calcium is least, then magnesium. After magnesium, you have beryllium, then strontium, and then barium. This was the actual order. This was the expected order. Because density of beryllium is higher than calcium and magnesium because of less volume comparison to its mass. So it's a combined effect of mass as well as size. Is that clear? Yes, Karthik, is that clear? Yes, right. Very good.
Yes.
Then you have the next two properties. Generally, S block metals and their salts give characteristic color to the Bunsen flame. Then flame causes an excitation of outermost electron, which on dropping back to the ground state emits the absorbed energy as visible light. So that is what is going to happen. So we have respect to nucleus, energy levels are present in this fashion, and we have outermost electron, and we are heating it. Because of heating, what happened? The outermost electron will be going to the excited state. The outermost electron, upon going to the excited state, it comes back to the ground state, releasing out some energy. Yes or no? Generally, S block metals and their salts give characteristic color to the Bunsen flame. The flame energy causes an excitation of the outermost electron, which on dropping back to ground state emits absorbed energy as visible light. Whatever the energy absorbed, that is going to be released back, because electron can't be stable in the higher energy state. It comes to lower energy state, because the energy which was in the lower energy, the electron which was in the lower energy state, it goes to higher energy state. It goes to higher energy state as it gain the heat energy from the respective heat. You are just heating the respective atom. What happened? The electron will take the energy from the heat. It will go to the higher energy state. Is it stable in the higher energy state? No. It want to come back to the lower energy state. If it comes to lower energy state, again it has to release out the absorbed energy, and that will be released in the form of some light. So for 1A, you have crimson red for lithium, sodium golden yellow, potassium violet, rubidium reddish violet, cesium blue. For 2A, beryllium and magnesium do not show color, because beryllium and magnesium, they have more effective nuclear charge. Because of that, they hold the outermost electron strongly. Because of that, the excitation of electron is not happening. Beryllium and magnesium, due to small size, bind their electrons more strongly, so are not excited to higher energy level, and hence no flame test. Beryllium and magnesium, no color. You may ask a question, sir, in beryllium and magnesium also we have electrons. No, I'll give more energy, so that I want to excite the electron to the higher energy level. Like there is some ionization potential defined, but I'll give more amount of energy so that the electronic excitation will happen. Then it will show, it has to show color or not? Yes or no? If you think logically, whatever the radiation we are giving, that radiation has to be taken by the outermost electron. That electron will excite, and it is not stable in the higher energy level. The electron de-excites, releasing out the absorbed radiation. If the electronic excitation happens with the visible range, then only you can see the color. If the excitation of beryllium is done by giving very high amount of energy, which is not at all in the visible range, then the excitation of electron may happen in some other range, but you cannot see any color because it is not in the visible region. Yes or no? This does not mean I cannot excite an electron. I can excite an electron by giving more and more energy. Whatever the, like, more and more amount of energy I will give from different kinds of sources, and I can excite the electron. But we will not see the color because the excitation is not happening in the visible range. So beryllium, magnesium, no color, and calcium, brick red, strontium, blood green, blood red, and barium, apple green. Okay, these are the respective colors. Understood or not?
Yes, sir.
The same color we have seen even in D block, if you remember. Like the electron lower energy states given the heat flame. So given the heat from the flame, so because of that, electron go to the higher energy state, not stable in the higher energy state, comes back to the lower energy state, releasing out radiation. Conductivity, you try to compare conductivity. 1A, due to presence of loosely held valence electron, which are free to move in metal structure, these elements are good conductors of heat as well as electricity. If you look at the conductivity, 1A and 2A, 2A is also a conductor or not conductor?
Conductor.
In 1A, due to the presence of loosely held valence electron, they can move in the structure. In the 2A also 2 electrons are there, right? 2 valence electrons. Those 2 valence electrons can be removed. So they can be also acting as conductors. Conductivity, you try to compare with 1A and 2A.
1A.
Why?
Because they will easily lose electron.
But the number of electrons will be great where? Number of free electrons.
In 2A.
2A, right? So 2A, number of free electrons are obtained more in 2A when compared to 1A. So because of that, conductivity mainly depends upon number of charged particles, like which are the number of charged particles, number of electrons present, which can the transfer of electrons is actually making it a conductor. So 2A, because of more number of free electrons or more number of valence electrons, so it will be acting as a better conductor. Conductivity greater for 2A when compared to 1A. Due to presence of loosely held valence electrons which are free to move in metal structure, these elements are good conductors of heat and electricity. These are also good conductors of heat and electricity due to the presence of two free electrons. So conductivity order, if you try to compare, 1A is less when compared to 2A. Yes, although you said that based on ionization potential, you can say that 2A, from 2A it is difficult to remove the electron, but ultimately more number of electrons are obtained from 2A, which will be responsible for more conductivity. That's the dominant factor. Chemical properties, conductivity in the gas phase also you can compare. Like this is the scenario in the solid phase. In the aqueous phase you can compare. Li plus
1A would have.
like within 1A, if you try to compare Li plus Na plus K plus Rb plus Cs plus, which will be better conductor
CS plus in aqueous phase.
in aqueous phase. Why?
Because it will be surrounded by less number of water molecules or solvent
Why?
molecules due to lower charge density.
Very good. Conductivity of 1A metal ions in aqueous phase will be decided based on hydration. Based on extent of hydration, which again depends upon charge density, right? Chemical properties, reactivity, reaction with air, reaction with oxygen, reaction with hydrogen, reaction with water, with halogen, reaction with nitrogen, solubility in liquid ammonia. All these chemical properties we are going to study one by one. First, let us think of reactivity, like 1A elements and 2A elements, which are more reactive.
1A.
Why? Because they can easily lose the electron. They can just lose one electron. So reactivity is inversely proportional to ionization energy. Greater the ionization energy, lesser is the reactivity. Lesser the ionization energy, more is the reactivity. And also amalgam formation. Reactivity, if you try to compare 1A elements, these elements are very reactive, so that is why they are not found in free states in nature. So if you try to compare the reactivity, reactivity is inversely proportional to ionization energy. Order of reactivity, you try to compare within 1A elements.
Li plus IR. Na.
Lithium is going to be order of reactivity, like which can be, yes, Li,
NaCS. Li, NaK, RbCS.
so increasing or decreasing. Cesium will be
Increasing.
most reactive because it can undergo the loss of electron very easily. So this will be the respective order of reactivity. Yeah, that is the order of reactivity is lithium, least, then sodium, potassium, rubidium, cesium. Lithium is less reactive, so reacts slowly with steam, while rubidium and cesium react even with cold water. So the reaction of alkali metal is very dangerous and vigorous. Very high amount of heat is going to be released. So be careful while you are dealing with such elements in the laboratory. Okay, that is why whenever you are doing Lassen's test, if you are doing Lassen's test, you will keep the sodium in the kerosene so that it will not be reacting with water to explode. Reaction of these alkali metals with water will be vigorous in nature. 2A, They are less reactive than alkali metals. Why? As they have high ionization potential, their reactivity will be less. Reactivity will be less. Order of reactivity: beryllium least, then magnesium. Like from top to bottom, reactivity is going to be increasing as ionization energy is decreasing. Beryllium do not react even with hot water. Magnesium reacts with hot water. Calcium, strontium, and barium, they can react with cold water. So from top to bottom, reactivity increases. From top to bottom, reactivity increases because the ionization potential is going to be decreasing. Right? Reaction with air: except beryllium, all S block metals are tarnished in air. Tarnished means they turn black. Like in dry air, only lithium gives nitride and oxide both, while other elements gives only oxides. Understand this point carefully. In dry air, only lithium gives oxides as well as nitride both, but remaining all they will give only oxides. Whereas on 2A, in dry air, beryllium, magnesium, and beryllium, magnesium, calcium, strontium, barium, all of them form nitride and oxide both. Yes or no? Lithium, the first element in the group 1A, it will only form both nitride and oxides. Nitride will be Li3N. In Li3N, we have Li plus and N minus 3 ion. Li2O, Li plus and O2 minus ion. Lithium forms normal oxides, and its oxide and nitride are obtained whenever lithium react with a respective air, whereas other elements they will not form respective nitrides. But 2A, if you try to think of 2A, in dry air, all the 2A elements they will form oxides as well as nitrides. In dry air, beryllium, magnesium, and all others form nitride and oxide both. So beryllium form respect to BeO, magnesium forms MgO, beryllium also form Be3N2, magnesium also forms Mg3N2. Generally, we can say, generally, the first elements in a group shows exceptional properties. Exceptional properties due to small size and high charge density and high polarizability, because they can try to attract the electron density present in the respective anions. Karthik, IE means ionization energy, IP means ionization potential. They both try to give idea regarding the amount of energy required to remove the electron from the outermost orbital. Both are same only. Okay. But whenever you're trying to apply those photoelectric graphs, there you have stopping potential, right? That potential is different. In the atomic structure, if you remember, we have drawn the graph with respect to stop, like electrons are obtained from the metal. Those are traveling through the positively charged plate and they are moving through the circuits. We are having external EMF, external potential. Because of this flow of electrons from the metal, some current is developed, that is nothing but photocurrent. That is nothing but photocurrent. To stop that photocurrent, we can again apply the potential in opposite direction, which is nothing but stopping potential. Yes, cesium can be giving out the, for cesium ionization energy is not highest. For cesium, ionization energy is going to be lowest because you can easily remove the electron from the outermost orbital. From the outermost shell, you can easily remove the electron from cesium, no, because very large in size. Because of that, its reactivity will be high. Okay. Ionization energy will be lowest for cesium because from top to bottom size increases. Because of increase in size, ionization energy will be decreasing. Because cesium has a lowest ionization energy, it is going to be highly reactive. Right. Reaction with air. These elements react with moist air to form carbonates as final products. That means these are the type of reactions you have. Sodium will be reacting with oxygen from the air to form Na2O. Generally, the major oxides which are going to be formed are lithium forms normal oxides, sodium form
Peroxide.
peroxides, and potassium, rubidium, cesium form
Superoxide.
Superoxide.
superoxide. Why only the heavier elements form superoxides? Because in superoxide we have what ion like KO2, K plus, O2 minus. In normal oxide we have O2 minus. In peroxide we have O2 2 minus. So superoxide ion O2 minus is a large size ion. So only the large size cations can actually neutralize or stabilize the superoxide ion. The small size Li plus or Na plus, they cannot stabilize O2 minus ion. Only the large size cations like K plus, Rb plus, Cs plus, they can stabilize the superoxide ion. Got that? But along with peroxide, sodium can also form normal oxide. Along with superoxide, potassium, rubidium, cesium can also form normal oxides and peroxides. But majorly they can form this difference properties is normal oxide, peroxide, and superoxides. And what happens? Na will be reacting with oxygen to form Na2O. Na2O is a normal oxide or peroxide?
Normal oxide.
Normal oxide. That Na2O react with water to form NaOH. That NaOH will be reacting with carbon dioxide to form Na2CO3. Dissolution of gas in a liquid can be studied. These elements react with moist air. Moist air means air which contain water to form carbonates Na2CO3 as the final product. To form carbonates as the final products. Right. Reaction with air. Except beryllium, these metals are easily tarnished in air. Why? Why not beryllium? Because in beryllium, a layer of oxide is going to be formed on the surface. If you think of this as beryllium, an oxide layer is going to be formed on the surface of beryllium, because of which it is not going to be reacting with air greatly. So except beryllium, these metals are easily tarnished in air. In moist air, except beryllium, all the elements convert into carbonates. In moist air, except beryllium, why can't beryllium? Because of the formation of layer of oxides. BeCO3 is unstable. The beryllium carbonate is unstable. BeCO3 is unstable. Why? Why BeCO3 is unstable?
Because it has higher covalent character.
Yes, Be plus 2 due to higher charge density can polarize the electron density of CO3 2 minus or not? Be plus 2. In BeCO3 we have Be plus 2 and CO3 2 minus, C double bond O minus, O minus. Be plus 2 because of higher charge density can polarize the electron density of CO3 2 minus, and thus leading to its unstable nature. Be plus 2 due to high charge density can polarize the electron density of CO3 2 minus, leading to its unstable nature. Reaction with oxygen. One elements, lithium forms oxide, sodium forms oxide and peroxide. As I have told you, lithium forms oxide only, normal oxide. Sodium forms normal oxide, and along with that peroxide can be formed, where all other forms oxides, peroxides and superoxides. Superoxides can be formed by only potassium, rubidium, cesium. Peroxide can be formed majorly from sodium. Lithium will be forming only oxide, normal oxide. So oxide means O2 minus ion is there. Peroxide means O2 2 minus ion will be there. Superoxide means O2 minus ion will be there. Superoxide means O2 minus ion will be there. And which are paramagnetic and which are diamagnetic?
Superoxides are paramagnetic.
Why? Oxides and peroxides, they are found to be diamagnetic in nature, whereas superoxides are paramagnetic and they are colored. Why? Oxides and peroxides are diamagnetic, whereas superoxides are paramagnetic and they are colored. Why? Because in a superoxide ion, that is O2 minus, the unpaired electron is present. There is an unpaired electron. Where is the unpaired electron present? There is an unpaired electron present in pi star antibonding molecular orbital. Yes, Suman, according to molecular orbital theory, the electron in O2 minus belong to the molecular orbital, not the respective atomic orbitals. So obviously the unpaired electron present in O2 minus ion, unpaired electron present in pi star antibonding molecular orbital of O2 minus ion. Pi star antibonding molecular orbital, right? Reaction with oxygen. Beryllium and magnesium form oxides, whereas others form oxides and peroxides in the 2A. The peroxides are diamagnetic but still colored due to lattice defects. Last class we have studied about lattice like a solid state, Frenkel defect and lattice defects. Yes or no? There, due to lattice defects, the color can be shown because electrons can also be trapped in the crystal lattice sites. Because of those trapped electrons, they will show color. Beryllium and magnesium form oxides, whereas others form oxides and peroxides. The peroxides are diamagnetic but still colored due to lattice defects. The stability order, this was the respective stability order. Normal oxide is more stable when compared to peroxides. Peroxides are more stable when compared to superoxides. Superoxides are stabilized only with the large size cations. Superoxides are stable only with a large size cations. Okay, only K plus, Rb plus, Cs plus, they form superoxides. In the 2A, beryllium and magnesium, they only form oxides, whereas others form oxides and peroxides. That means in 2A, superoxides are not generally formed because of their small size. And if you try to compare the order of stability, normal oxide is more stable when compared to peroxide. Peroxide is more stable when compared to superoxide. Superoxide electronic repulsions are also there. Right? These are respect to order of stabilities. Reaction with oxygen, like lithium forms normal oxides, sodium forms normal oxide and peroxide, potassium, rubidium, cesium, they form normal oxide, peroxide as well as superoxide. In a group 2A, beryllium and magnesium, they form normal oxides, and calcium, strontium, barium, they form respect to MO2. That is, MO2 means what? MO2 means M2 plus ion is there along with O2 2 minus ion is there. So MO2 is a peroxide or superoxide here?
Peroxide.
Peroxide. MO2, if I write in 1A, that is a peroxide or superoxide? If I write MO2 in 1A, it will have M plus and O2 minus ion. So MO2 is
Superoxide.
If M is 1A element, MO2 is peroxide. If M is 2A element, because MO2, because in the 2A M will be having plus 2, because M is in plus 2, O2 2 minus is there. So MO2 is peroxide if M is 2A element, MO2 is superoxide if M is 1A element. And they form superoxides of time M plus 2 and O2 2 minus. O2 2 minus is nothing but peroxide ion. Peroxide anion. Normal oxide, peroxide, superoxides are going to be formed by 1A, like lithium form normal oxides, sodium normal oxide and peroxide, potassium, rubidium, cesium, normal oxide, peroxide as well as superoxide. Beryllium, magnesium only normal oxide, calcium, strontium, barium only peroxide. In the group 2A, superoxide is not formed because of smaller size. Is everything clear so far?
Yes.
Yes.
Yes, right. Try to look at the reaction with hydrogen. Reaction with hydrogen, 2M plus H2 forms 2MH. The metal hydride react with water to give MOH and H2. M plus MH plus H2 gives MOH plus H2. Like metal hydride, if you take metal hydride M plus and H minus, the metal hydride's H minus ion will be reacting with a partial positively charged hydrogen from water, developing respective H2 gas. The metal hydride react with water to form MOH and H2 in case of 1A elements. If you take 2A, they will form what? Metal hydride you take MH. Like in the 2A, what you are going to have? MH2 will have, right? In the 2A, they form hydrates of the type MH2, where we have M plus 2 and 2 H minus. These H minus will be reacting with the respective water to form H2 gas, M plus 2 and 2 H minus. This H minus will be reacting with H2O, 2 H2O to form H2 gas. How many H minus will react with the H plus to form H2? 2 H minus will react with H plus to form 2 H2. Along with the 2 OH minus is released out. 2 OH minus will be reacting with M plus 2 to form what? MOH.
MOH voltage.
Yes or no? That is how the respective hydroxides are going to be formed with respect to 2A. M plus H2 will form MH2. The metal hydride react with water to give MOH taken twice and H2. MH2, like you can write the reaction as MH2 plus H2O, 2H2O will be forming MOH taken twice plus 2H2. Check out the balancing parts. 6 hydrogens, 4 plus 2, 6 hydrogens, 1 metal, and 2 oxygens and 2 oxygens. That is how the reaction can be written. MH you cannot write, no, because M is an alkaline earth metal, means it will form hydrates of the type MH2, not MH. So this is wrong. Reaction with water, reaction with air, reaction with hydrogen, and the reaction with water. And the reaction with hydrogen is generally happening at high temperature. Why? Because the bond between two hydrogen atoms that has to be broken. The bond between two hydrogen atoms is formed by the overlapping of 1s atomic orbital of one hydrogen with 1s atomic orbital of another hydrogen. That 1s overlapping will be stronger. Because of that, the reaction is going to happen only at high temperature, because the bond between two hydrogen atoms has to be cleaved. Reaction with water, 1A elements as well as 2A elements, they react with water, like respect to 1A elements and 2A elements, they react with hydrogen to form hydrides. They react with water to form, they react with the hydrogen to form hydrides, and they react with water to form respective hydroxides. The same reactions we have written earlier now. Like metal hydrides reacting with water, we have seen. Metal hydrides reacting with metal hydride reacting with water to form hydroxides. Similar type of reaction is going to be seen with the metals reacting with water also. Like metal reacting with water, metal forms what? Metal will form respect to M plus and electron is lost. And 2H2O, H2O will have H plus and OH minus ions. H plus will take up an electron to form hydrogen atom. 2H plus will take up 2 electron to form H2 gas. And OH minus will be reacting with M plus to form respect to MOH. This is how the reaction you can happen with 1A. Reactivity with water, lithium is going to be least reactive, Sodium reacts vigorously. Yes or no? Lithium is going to be least reactive towards water. Why it is least reactive? Even though standard oxidation potential of lithium is highest, it will not react with water vigorously. Why? Like if you compare Li plus electron gives rise to Li, it will have some weight. SRP is lowest. That means lithium has a tendency to convert to Li plus at a greater tendency. Even though standard oxidation potential of lithium is a highest, it reacts less vigorously with water. It reacts less vigorously with water due to more hydration. Due to more hydration. Group 2A, if you try to compare, metal will be reacting with water to form MOH taken twice plus H2, and the reactivity with water will be increasing from top to bottom. Beryllium least, then magnesium, calcium, strontium, and barium. Beryllium do not react with water because of the oxide layer formation. Beryllium reacts only with like magnesium reacts only with the hot water. Like increasing from top to bottom. Like if you go from top to bottom, the reactivity with water is also going to be increasing. Reactivity with water, that will be increasing if you go from top to bottom in that particular group. Is that clear or not?
Yes, sir.
Sir.
That's right. Reaction with water, if you think of potassium, that reacts with water producing a flame. Rubidium and cesium, they react explosively. Calcium, strontium, barium react with cold water, but not as energetically as alkali metals. Why? Alkali metals will have lowest ionization potentials. Because of low ionization potentials, they can immediately react with water because of that conversion of cesium to cesium plus. You can see videos as well where the alkali metals are reacting with water, like a chunk of alkali metal is added to a small water body. Yes or no? And there different types of reactions are being seen. And the basic strength of oxide or hydroxide, if you try to compare, order of basic strength, LiOH, NaOH, KOH, RbOH, CSOH. So if you try to think of Li plus and OH minus ion, basic nature will be more whenever we have more ionic character. Basic nature is directly proportional to basic nature of hydroxide is directly proportional to ionic character. Basic nature of hydroxide is directly proportional to ionic character, and it is inversely proportional to covalent character. Basic nature of hydroxide is directly proportional to ionic character. Wherever we have more ions, they like more OH minus ion present means more basic nature. So more ionic character means more basic nature, or less covalent character means more basic nature. Less covalent, where we have less covalent character, or where we have more covalent character, you try to argue. More covalent character, LiOH, because the first elements, because of more charge density, they will try to attract the electron density of OH minus to be shared. Because of that more covalent character, they will have less ionic character, less basic strength. So this is the order of basic strength. You go with this logics instead of this. Basic strength of oxide or hydroxide, that should be directly proportional to ionic character, which is inversely proportional to covalent character, or you can say which is inversely proportional to electronegativity of central metal atom. Reaction with halogens, they will react with halogens to form respect to halides. Like sodium will be reacting with the chlorine to form NaCl. Calcium will also react with the chlorine to form CaCl2. And what idea we can say is, these halides, whatever are going to be obtained from group 1A as well as group 2A, they are water absorbing in nature. Because of more charge density, I can say the halides of lithium and group 2A metal halides, they are always present in hydrate form, whereas NaCl, KCl, CSCl, RbCl, they are not present in hydrate form. They react with halogens. 2m plus x2 upon high temperature forms 2mx because the temperature will be helping in cleaving the bonds, making the reaction occur greatly. M plus x2 will form mx2. M is a group 2a metal. M here is a group 1a element. So 2Na plus F2 will form 2NaF. Ca plus Cl2 forms CaCl2. And we have lithium chloride and all 2a metal chlorides are hygroscopic in nature. Why? Because of more charge density. Because of more charge density, the extent of hydrogen is great. Charge density, the extent of hydration. The extent of hydration is high. Is that clear or not? Lithium chloride and all the group 2a metal chlorides, they will form hydrated chlorides because they are having more charge density. Their extent of hydration is great. And in all these metal halides, you can apply Fazan's rule to understand the covalent character. Metal halides, we can apply Fazan's rule. Anyone can say Fazan's rules?
Metal with more charge density will polarize the anion, thereby increasing the covalent characters.
Very good. And with respect to change in cation, change in anion?
Higher, greater the size of anion, more will be the polarized.
Very good. So whenever we have a cation with more charge density for same anion, it will have more covalent character. For the same cation, the anion with large size, it will have more covalent character because polarization of electron density is easy. In all these metal halides, we can apply Fazan's rule to understand covalent character. Right? Potassium, rubidium, cesium halides, they will react with halogen to form polyhalide ionic compound. Like if you take an example, Ki plus I2 will form Ki3, where Ki3 exists as K plus and I3 minus ion. What is the structure of I3 minus ion?
Linear.
Linear in shape. Linear in shape. Same with respect to cesium also. Cesium iodide will be reacting with I2 to form CsI3. CsI3 will exist as Cs plus and I3 minus ion. Like polyhalide ionic compound is going to be formed, and I3 minus will be existing as linear molecule. Okay. I3 minus will be existing as a linear molecule or linear structure it will have. Which of the following oxide has O2 minus 2 peroxide anion? Na2O will form respect to peroxides. The paramagnetic species is
KO2.
KO2. It is paramagnetic due to the presence of unpaired electron in respect to pi star antibonding molecular orbital. Reaction with N2. Reaction with N2, nitrogen has a triple bond between two nitrogen atoms. In N2 gas, we have a triple bond between two nitrogen atoms. So only lithium will be reacting with N2 to form nitride, whereas other elements will not react. This lithium nitride will react with water to form lithium hydroxide and ammonia is evolved. Whereas all group 2A elements, they can react with nitrogen to form nitrides, which again on hydrolysis will form ammonia. Like lithium will be reacting with a nitrogen N2 to form Li3N. This Li3N will be reacting with water. Li3N will have Li plus ions and N minus 3 ions. We have what? Li plus ions, 3 Li plus ions and N minus 3 ions. This N minus 3 will be obtaining proton from 3 H2O molecules forming NH3. Along with that, we have OH minus released out, right? Because it has H plus and OH minus. So Li3N will react with 3 H2O. So 3 H plus and 3 OH minus, you will form 3 LiOH. Clear or not? Like that, the reaction is going to happen. Same type of reaction with the group 2A also. Ammonia is going to be evolved. Only lithium reacts directly with N2 to form nitride, which gives NH3 ammonia upon reacting with water. Other elements of group 1A, other elements of group 1A will not react with N2 to form nitride. Lithium will react with nitrogen to form nitrides, and all elements of group 2A, they will react with nitrogen to form respect to nitrides. Those nitrides, upon exposure to water, they form respect to hydroxides. And this was how the mechanistic approach you can understand. Not the mechanistic approach, but a simple ionic mechanism. Solubility in liquid ammonia. If you try to think of solubility in liquid ammonia, like what do we have? Alkali and alkaline earth metals, except beryllium and magnesium, they dissolve in liquid ammonia, that is high concentration of ammonia, and give blue colored solution. Like if you think of any metal, the metal will be forming respect to M plus ions. Like if you take alkali metal, it will form respect to M plus ion and electron is leached out. Let us say metal M is reacting with X plus Y mole of ammonia. Metal M is giving M plus and electron. We have X plus Y mole of ammonia. Ammonia has lone pair of electron. Let us say X moles of ammonia will develop electrostatic attraction with M plus ion, because ammonia has a lone pair of electron. It can attract the respect to M plus. That will form what? M NH3 taken X whole plus, and these electrons, whatever is present, right, they will also be coordinated with ammonia. The electron will also be coordinated with ammonia, but ammonia already has lone pair of electron. Electron repulsion will be there. Although electron repulsion is there, the arrangement will happen in such a way such that around electron, the partial positively charged nitrogens, they will be near the electron, and lone pair of electron present on nitrogen, that will be away from the electron. This is how the ammoniated electrons are present. The partial positively charged hydrogens, they are closer toward the ammoniated electron, and nitrogen with a lone pair, that will be far away from the electron to maintain minimum repulsion. These ammoniated electrons, they were actually responsible for color. Many properties are there. Like this solution will be highly reactive. We'll study all the properties now. Metal, if you try to add to water, it will give M plus and electron. Around the electron, all the ammonia present, and about the M plus also ammonia present. If you look at M plus, around M plus ammonia are present in such a way such that nitrogen's lone pair is closer toward the M plus. Around the electron, the partial positively charged hydrogen is closer toward the electron. Nitrogen is away. And this is nothing but a solution. Solubility in liquid ammonia, it is highly reactive solution. High reducing power, that is due to what? Ammoniated electrons. And it is going to be paramagnetic in nature, again due to ammoniated electrons. The color of the solution, again due to ammoniated electrons. Only the conductivity, that is due to both the ions as well as ammoniated electrons. That is why it is said to be solution of alkali or alkali metals in liquid ammonia. Alkali or alkaline earth metals in liquid ammonia. That is why solution of alkali or alkaline earth metals in liquid ammonia is a mixed conductor. We have given the example of mixed conductor in electrochemistry as well, if you remember. Electrolytic conductor, metallic conductor, mixed conductor. Mixed conductor means the conductivity is due to motion of ions as well as electrons. Only lithium form imide. So lithium will be reacting with ammonia to form Li2NH, lithiumide, and that will release the H2 gas. Lithium will be reacting with ammonia to form Li2NH. Whereas other compounds, they will be reacting like sodium, calcium, cesium, they will form respect to amides. Lithium form imide. Sodium, like upon long standing, they will form respect to amide. M plus ions reacting with ammonia to form MnH2. MnH2, NaNH2, CsNH2, BaNH2 taken twice. So these amides, they are going to be acting as a very strong basis. On standing, the color fades due to the formation of amides. Whatever the solution we have, upon long standing, the color is going to be fading. Why? Because the respective amides are going to be formed. M plus NH3 will form MnH2, where M can be sodium, cesium, calcium, strontium, and barium. Na plus NH3 will form NaNH2. The respective amides, sodamide or amides are very strong bases, and they can be useful in organic chemistry, and they are useful in many organic reactions. Notice, if the concentration of metal increases, then due to formation of cluster of metal ions, solution shows metallic bronze color, and the paramagnetic character of the solution, that will also decrease. Whenever you have very high concentrated, solution shows respective cluster formation, that is bronze color is also going to be shown, and paramagnetic character of the solution, that will be decreasing, because the cluster is going to be formed instead of forming more number of ammoniated electrons, right? Amalgam formation. Alkali metals form amalgam with mercury, and alkaline earth metals, they also show some properties. That means they also form amalgam. Like sodium, whenever you try to look at the electrolytic reduction of a brine solution, we have Na plus and Cl minus ions. Whenever the electrode is mercury, what happens? The Na plus will reach the respective mercury electrode and form the amalgam formation. There you do not compare the respective standard electrode potential values, because the reduction of sodium in the presence of mercury electrode, that will be happening easily to form, like the reduction potential has been decreased, like easily reduction of Na plus can be done. Na plus will take up the reach the respective mercury cathode, and there you will have the sodium amalgam formation. Is that clear, students?
Yes, sir.
Yes, right. And after this, we have different compounds of S block elements. What are different compounds we have to see is sodium chloride, sodium hydroxide or caustic soda, NaHCO3, sodium bicarbonate or baking soda, Na2CO3, sodium carbonate or soda ash, calcium oxide or quicklime, calcium hydroxide or slaked lime, calcium sulfate or dead burns plaster, CSO.half H2O, hemihydrate of calcium sulfate, or you can say that as plaster of Paris, and cement. So these are the different commercially important compounds of S block elements. We'll study one by one. NaCl, sodium chloride. Occurrence, from where you will be getting respect to NaCl. NaCl is mostly obtained from the seawater.
Oceans.
Yes, sir. Seawater is ocean, seawater, all that is a major source of NaCl, and is also found in salt lakes. Preparation, if you take, you have to just try to take the seawater and do the evaporation by solar heat. You will get crude NaCl. Crude NaCl means it will be having lot of impurities which you have to remove. So it contains impurities of many other electrolytes like sulfates, chlorides, also like magnesium chloride, calcium chloride, sodium sulfate. Like that we have impurities. The insoluble impurities you can remove by filtration. The soluble impurities you have to do like ion exchange method. After that only the soluble impurities you can be removing. So sea water you take, you do the evaporation. By solar heat you will get crude NaCl. NaCl you have. If you try to evaporate the sea water by solar heat, you will be getting respect to NaCl. It contains these impurities like Na2SO4, MgCl2, CaCl2. Insoluble impurities, whatever the insoluble impurities we have, they can be removed by filtration, whereas soluble impurities, for the removal of soluble impurities, special techniques were used like ion exchange resins were used. Insoluble impurities, they are removed by filtration. MgCl2 and CaCl2 are more soluble in water because of more charge density of Mg plus 2 and Ca plus 2. The solubility is going to be high. So they left out in the solution in the soluble form. Because they are left out in the solution in the soluble form, what you have to do? We have to remove them by using special techniques like ion exchange method. If we try to remove them only, then only we will be getting the respective pure NaCl. In the water itself, we have NaCl, MgCl2, CaCl2. The MgCl2, CaCl2 we have to remove by different techniques like ion exchange methods and all. Or you can just remove the Ca plus 2 and Mg plus 2 ion. Like hardness of water we have removed, right? We have water, along with that we have NaCl, CaCl and Mg plus 2. Mg plus 2, Ca plus 2, Na plus ions are there. These Mg plus 2 and Ca plus 2, they can be removed by Kalgan or also by the respective sodium aluminate. Yes or no?
Yes,
It's
sir.
permitted methods. Yes. So NaCl, sodium chloride properties, stable salt is slightly hygroscopic due to the presence of magnesium and calcium chlorides in small amounts. The magnesium and calcium, whatever they are present in small amounts, because of that, it is going to be slightly hygroscopic in nature. Hygroscopic means it will try to attract the water. That means it will remain in the hydrated form. And reactions, what type of reactions are going to happen? Reaction with AgNO3 and chromyl chloride test. NaCl, Na plus Cl minus react with AgNO3 to form NaNO3 and AgCl. This is a very fast reaction. The kinetics of very fast reaction can't be studied because it is a formation of precipitates. As soon as you try to add NaCl and AgNO3, immediately you will be respectively getting the AgCl, which was a white precipitate. Chromyl chloride test, chromyl chloride, that is CrO2Cl2, orange reddish colored CrO2Cl2 is obtained. That is a test to actually detect the chloride ion. So NaCl plus K2Cr2O7 plus 5H2SO4 upon heating forms NaHSO4 plus K2SO4 plus CrO2Cl2. So it is a test used to detect the chloride ion. Okay. We can detect the chloride ion as well using this test. We can detect the chloride ion using this particular test. So these are the properties of NaCl and different types of reactions. If you go with next to commercially important, NaCl is mostly used, right? NaCl major source is seawater only. We do the evaporation of seawater by heat and then produce NaCl. Whatever the insoluble impurities we have, we will remove them. And soluble impurities we try to remove the Mg plus 2 and Ca plus 2 because we have to produce pure NaCl. And also due to the presence of small quantities of Mg plus 2 and Ca plus 2, NaCl is hydrated. Next, sodium hydroxide or NaOH or caustic soda. Manufacture, if you try to think of, by electrolysis of NaCl. If you take NaCl, NaCl will have what? Na plus and Cl minus ions. Using the electrolysis of NaCl, you can actually produce NaOH. Nelson or diaphragm cell. So NaCl dissociate to give Na plus and Cl minus ion. And along with Na plus we have water. Along with Cl minus also we have water. When compared to NaCl and water, like water also dissociate to produce H plus and OH minus. Water also dissociate to produce H plus and OH minus ions. Na plus and H plus competition, Cl minus OH minus competition. So at a cathode, what happens? Cathode is negatively charged. So positively charged Na plus and H plus ions move. So when compared to Na plus, H plus will deposit. That is, H plus will be reaching the cathode fastly based on SRP values. H plus will take up the electron to form H2 gas. And chloride and OH minus, when compared to OH minus, chloride will reach the respective anode forming Cl2. So H plus will be taking up 2 electrons. 2H plus will take up 2 electrons to form H2 gas. This happens at cathode. At anode, what happens? 2
Chloride.
Cl minus will form Cl2 and 2 electrons are obtained. And what are left out in the solution? We have Na plus ions left out
Sodium
and OH minus ions left out, which is nothing but sodium hydroxide. Cl2 is actually obtained, Cl2 and H2, they were actually obtained as side products. At a cathode, we have respect to H2 gas released. At anode, we have respect to chlorine gas evolved. Thus, Cl2 is obtained as a byproduct in the preparation of NaOH. Cl2 is obtained as a byproduct if you look at the preparation of NaOH. Is that clear?
Yes, sir.
The next type of cell is Kastner-Kellner cell. We will discuss about this Kastner-Kellner cell and the other properties in the next class. Thank you all, everyone. Bye.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.